In this video we look at the FP1 work on transformations. In particular, we are going to be looking at translations, rotations and reflections and how they can be represented in terms of matrices. So for the key facts, if we have a transformation given by the matrix ABCD, then the image of the origin is always going to be the origin. The image of the point 1, 0 is AC, and the image of the point 0, 1 will be BD. There are two particular cases that we need to know for transformations. That is the rotation of angle theta anticlockwise about the origin, and also a reflection in the line y equals tan theta times x. And these two results you'll be able to find inside your formula booklet. If we know that a transformation S has the matrix A and transformation T has got the matrix B, then the transformation S followed by T has got matrix BA, and be very careful about the order of the two matrices there. We should know that a translation of the plane cannot be written in terms of a 2 by 2 matrix, but it can be written using a 3 by 3 matrix. Furthermore, we should realise that a 3 by 3 matrix can be used to give a transformation which is equivalent to the transformation with a 2 by 2 matrix ABCD followed by a translation of PQ. Finally, we must understand what is meant by a fixed point. Fixed point is a point that is left alone by the transformation. So algebraically, if the transformation is represented by a 2 by 2 matrix, then we must have ABCD times alpha beta equals alpha beta. If on the other hand the transformation is represented by a 3 by 3 matrix and alpha beta is a fixed point, then we must have the matrix times by alpha beta 1 must equal alpha beta 1. So let's have a look at some exam examples now. So this first one comes from the June 2010 paper. We're told that the transformation T consists of an anti-clockwise rotation through 90 degrees followed by a translation of -3 in the x direction and +1 in the y direction. So we know that the matrix for a rotation takes the form cos theta minus sine theta as the top row, sine theta cos theta as the bottom row of the matrix. That's in the formula booklets. So making use of the fact that theta is 90 degrees, we've got the matrix for the rotation is 0, -1, 1, 0. So the point xy under the rotation will be taken to the point given by that matrix multiplication, which is -yx. If we then follow that up with the translation of -3 in the x direction and 1 in the y direction, we will end up with our final image being the point -y -3 as the x coordinate and x plus 1 as the y coordinate of the final point. So the point xy1 has ended up as -y -3 x plus 1 1, and we can represent that in terms of the matrix 0, minus 1, minus 3, 1, 0, 1, 0, 0, 1 times x, y, 1. So the matrix representing the transformation is the one that we were given. Moving on to the second part of the question, we have to find the fixed point of t. So if alpha beta is a fixed point of t, then that means that when we apply our matrix to the vector alpha beta 1, we must get the answer alpha beta 1. So performing the multiplication, we've got minus beta minus 3, alpha plus 1, 1 must equal alpha beta 1. So we've got, looking at the x coordinates, getting everything onto the right hand side, we've got 0 plus alpha, 0 must equal alpha plus beta plus 3. And looking at the y coordinates, we've got beta minus alpha minus 1 must equal 0. So we've got a pair of simultaneous equations to solve there. We can solve those by any of the standard methods for simultaneous equations. In this case, if we add the two equations, we will end up with 2 beta plus 2 must equal 0. So beta must be minus 1, and if beta is minus 1, then alpha is going to be minus 2. So we found out the fixed point is the point minus 2, minus 1. So for the final part of the question, we're told that the image of the line L under t has got an equation of x plus 2y equals 3. We've got to find the equation of L. So let's start with an arbitrary point x, y, and suppose that under the transformation t it ends up as being x dash y dash. Then we can find x dash and y dash using the relationship that x dash y dash 1 must equal the matrix times by x, y, 1. In other words, when we carry out the multiplication, we've got x dash y dash 1 must be minus y minus 3, x plus 1, 1. So we know that x dash must be minus y minus 3, and y dash must equal x plus 1. But we know that the image point lies on the line x plus 2y equals 3. So in other words, we know that x dash plus 2 times y dash must equal 3. And that implies that minus y, take away 3, that's the value of x dash, plus 2 times x plus 1, that's the value of y dash, must equal 3. And if we tidy up the algebra on that, we've got 2x, take away y, must equal 4. So that must be the equation of the line L. Considering the mark scheme for this question, the first part of the question, there was 1 mark for obtaining the rotation matrix, 1 mark for handling the translation, and then a final mark for justifying the final 3x3 matrix. For part B, finding the fixed point, we need to establish the pair of simultaneous equations, which gave us the first 2 marks, and solve them for the final 2 marks. And then for part C, we need to establish the formula for x dash and y dash for the first 2 marks, and then make use of the fact that x dash plus 2y dash equals 3 to obtain the equation of L for the final 2 marks. Moving on to our second example, which comes from the 2009 January paper. We're given a transformation which we are told is a rotation, and we are given the matrix. So the first thing we've got to do is find the coordinates of the fixed point of t. So if we suppose that alpha beta is the fixed point, then the matrix times the vector alpha beta 1 must equal alpha beta 1. So performing the matrix multiplication, we've got 0.6 alpha plus 0.8 beta plus 2 must equal alpha. That's looking at the top row. And we've also got minus 0.8 alpha plus 0.6 beta plus 3 must equal beta. That's looking at the second row. Don't need to worry about the bottom row, it will simply tell us that 1 equaled 1. Tidying up those 2 simultaneous equations, we can rewrite them as 2 equals 0.4 alpha minus 0.8 beta, and 3 equals 0.8 alpha plus 0.4 beta, and using any standard method for solving the simultaneous equations, we obtain alpha equals 4 and beta equals minus 0.5. So the fixed point of the transformation t is the point 4 minus 0.5. We've now got to determine the centre and the angle for this rotation. Well, if we perform a rotation, the only point that stays fixed under a rotation is the centre point. So the centre point is going to be the fixed point that we've just found, which is 4 minus 0.5. If we're going to find the angle of the rotation, one way of doing this would be to take a point close to the centre and find out what angle it turns through. So what we might do is we might consider the point which is 1 unit in the x direction away from the centre of the rotation as our object point. We can calculate the image of this point under the transformation by performing the matrix multiplication. So we've got the matrix times 5 minus 0.5, 1, and performing the multiplication we end up with the point, the vector 4.6 minus 1.3, 1. So the image point is 4.6 minus 1.3. Now if we represent this diagrammatically, we've got the centre was the point 4 minus 0.5, we had the object was the point 5 minus 0.5, and the image point was the point 4.6 minus 1.3. And we can see from our sketch that we have done a clockwise rotation of angle theta. Looking at the coordinates of the centre of the rotation and the image point, we can see that the image point is 0.8 units below the centre, and that the image point is 0.6 units to the right of the centre point. Now those two values give me enough to determine the value of theta. So we've got tan theta must be 0.8 divided by 0.6, so theta must be 53.1 degrees. So we have the angle of the rotation is 53.1 degrees in a clockwise direction. The marks for this question, well, for part A there were 4 marks, which would be probably split 2 marks for setting up the pair of simultaneous equations for the fixed point, and then 2 marks for solving them. And then for part B, 1 mark for simply observing that the centre of the rotation was in fact the fixed point that we just found, and then 3 marks for determining the angle of the rotation. Let's now move on to our final transformations example, which comes from the 2013 January paper. And in this case, the transformations are being represented by 2x2 matrices rather than by 3x3 matrices. So, if A is the matrix for a rotation of 45 degrees anti-clockwise about the origin, then using the result in the formula booklet, we can say that A must be cos 45 minus sin 45, sin 45, cos 45, and we should know that cos 45 and sin 45 are both equal to 1 over root 2. The line x plus y equals 0 can of course be written as y equals minus x, or if you like, y equals minus 1 times x, and minus 1 is of course the value of tan minus 45. So we've got a reflection in the line y equals tan minus 45 degrees times by x. So again, using the standard result given in the formula booklet, we can say the reflection matrix will be cos of minus 90, sine of minus 90, sine of minus 90, minus cos of minus 90, which ends up just giving us 0, minus 1, minus 1, 0. Now T is the effect of doing the rotation represented by matrix A, followed by the reflection represented by matrix B. And the single matrix for T will therefore be BA. And again, we just need to be careful that we get the order of these two matrices right. So B times A is that matrix product, which may be evaluated to obtain the matrix that we were aiming for. So we have shown that that is the matrix for the transformation T. Moving on, we've got to find the equation of the image under the transformation T of the line y equals m times x. Well, a typical point on the line y equals mx will simply be a point whose coordinates are x equals alpha and y equals m times alpha. If we want to find the image of this particular point, we need to do the matrix multiplication, and we'll obtain 1 over root 2 minus alpha minus m alpha as the x value, minus alpha plus m alpha as the y value. If we call the image point x dash y dash, then we've got x dash is minus m plus 1 times alpha over root 2, and y dash is m minus 1 times alpha over root 2. Now you'll notice that both of these expressions have got alpha in common, and have also got a divisor of root 2 in common. So it might be worth just considering y dash divided by x dash, because if we consider y dash divided by x dash, the alphas will cancel each other out, the root 2's will cancel each other out. So we've got y dash over x dash is m minus 1 over minus m plus 1. In other words, we've got y dash equals m minus 1 over minus m minus 1 times by x dash. And that is the equation of the image line. Finally, we're told that the line y equals mx is actually transformed onto itself. So that means the image line is the same as the original line, y equals mx. And if the image line is the same as the original line, the gradient of the image line must be the same as the gradient of the original line. So we can say that m, gradient of the original line, must be the same as m minus 1 over minus m minus 1. Multiplying up to clear the fractions, we obtain minus m squared minus m equals m minus 1. Collecting all the terms on the right hand side, we've got 0 equals m squared plus 2m minus 1. So we've got a quadratic equation for m, and that quadratic equation can be solved in any of the standard methods for quadratic equations, and we obtain m as being minus 1 plus or minus the square root of 2. Now the marking for this question, there's been 1 mark for obtaining or writing down the rotation matrix at the beginning of the question, 1 mark for the reflection matrix, and then 1 mark for ensuring that T did indeed have the required matrix. For the first part of part B, we needed to obtain the coordinates of the image point, which gave us our first 2 marks, and then we needed to make sure that we eliminated the alphas, so we needed to do that division to obtain the equation of the image line, which then gave us another mark. And then for part 2, we needed to equate the 2 gradients for the first mark, obtain the quadratic equation, and solve it for the final 2 marks.